So I'm very bad at speeches, so that's my way to show my love and say thank you for all the things you did for me. Just don't tell my dad about that, right? Okay, so yeah, so I will talk about this new approach for principal-agent problem. So this has been developed with my PhD student at Orphy. So first I will talk a bit about principal-agent problem so that we all know what it is. And then I will explain the new approach towards some kind of first illustrative example. Then probably I will talk just a little bit about the more general model. And then hopefully I will have time to talk about some extension to multi-agent problems. Okay, so the goal of these principal-agent problems, I'm sorry, René, you heard this talk a lot and these slides. But so the goal is to analyze this interaction between economic agents and in particular with asymmetric information. So in particular here we'll consider this kind of mole hazard framework. So the goal is that, you have a principal who's going to offer a contract for an agent. This contract has a finite time horizon, capital T here. And so the contract is basically represented by some kind of terminal payment that's going to be optimally designed by the principal and paid to the agent at the end of the contracting period. And the agent is not a slave, so he can accept or refuse the contract that is offered by the principal. So the principal goal is to find an optimal contract, optimal in the sense that it's going to maximize the utility of the principal and such that the agent is going to accept it. So there are a lot of paper on this. So before the first one, so before Armstrong and Milgram, there were mostly like discrete time study of this type of problem. And so the Armstrong and Milgram paper was basically the first model in continuous time. Then there were this paper by Sannikov who developed some kind of general methods to solve this continuous time principal agent problem, basically using the continuation utility of the agent. Okay, and more recently there were this approach by Nizar, Dilan, and Yaksha who extended basically the approach by Sannikov to make it more general, more rigorous, and especially to be able to tackle this volatility control problem. So basically the method has kind of 3 steps. The first one is to identify some kind of nice form of contract so that if you put it in the agent's utility, then you can easily compute what's going to be the best response of the agent to that type of contract. Then, of course, you have to prove that this nice form of contract is without loss of generality from the principal point of view. And then finally, you have to solve the principal's problem, but using this nice form of contract, it usually boils down to some kind of standard stochastic control problem. Okay, so the framework, the general framework is usually that one. So you have a process X that is controlled by the agent through some kind of effort nu here. And so this effort nu can impact the drift and the volatility of the process, basically. Okay, and this mole hazard feature, so the asymmetry of information between the principal and the agent, is represented by the fact that the agent is going to choose this effort, but the principal cannot observe the effort. The principal will only observe the process X in continuous time. Okay, so just to formalize things here a little bit, so the agent is going to try to solve some kind of maximization expected utility kind of problem. So he's going to receive this payment psi and have some kind of cost of effort to pay. Okay, and so the goal is to find an effort that would maximize this expected utility. And then the goal of the principal is to find the optimal contract, so anticipating what's going to be the best response of the agent to that contract. Okay, so I already mentioned a bit the existing approach, so namely the one by Sannikov and then the one by Nizar, Yaksha, and Dilan. So the one by Sannikov kind of only allows to tackle this drift control case, so when the volatility is not controlled. And in that case, basically the idea is to look at the dynamic value function of the agent and to relate it to the corresponding BSDE. Okay, so basically the terminal condition of the BSD is going to give you the form of the contract. Okay, so here you have kind of the form of the contract. So basically in the Lebesgue integral is the integral of the Hamiltonian, so that's the standard thing in stochastic control. And then you have the most important part, so the Ito integral on z dx. So that's the part that's going to incentivize the agent to make some effort on the drift, basically. Okay, and so basically the idea is that instead of, when you look at the principal problem, instead of looking at every possible form of contract, you can just restrict to that form of contract. These are going to be the optimal form. And so that makes the problem of the principal way more easy to tackle, because the principal just have basically to choose this process Z in the contract. Okay, now if you go to the volatility control case, same, the idea is to find this nice form of contract. So the form of contract is that one here. So same, you have this Hamiltonian part. Now in there you have basically to take into account this volatility control, but that's the Hamiltonian will have in stochastic control also. You still have the z dx integral that's going to incentivize the agent to make some effort on the drift. And finally, you have an additional part here, which is the gamma d bracket of x integral. So this gamma is an extra parameter that can be chosen by the principal also. And basically, this part of the contract is going to incentivize the agent to make some effort on the volatility. Okay, and so the difficulty here compared to the drift case only is that if you want to prove that this form of contract in the volatility case is optimal, then you would have to go through second order BSD. Okay, so because of volatility control, now this dynamic value function of the agent can be represented as a second order BSD. Okay, so basically, so the main idea of the approach that I'm going to present just after is to see how we can kind of bypass this second order BSD kind of issue. Okay, and there are many applications of this principal agent problem of volatility control in the literature. I'm mostly citing work from Nizar and René Aids, not you, the other René. But there are some application in finance or in energy, for example. I mean, we also think that there could be more application if the solution was easier, right? So hopefully having an easier method would allow to tackle more application. And so in terms of extension, people have looked at multi-agent problems, so where you have one principal and many agents that can work for the principal, or extension to some kind of continuum of agents with this mean field interaction, for example. And also people are also considering output processes with jams. The problem with this extension is that then you have to look at second order BSD that are either multidimensional or some kind of mean field type second order BSD or second order BSD with jams. And the full theory is not there yet to be able to completely and rigorously tackle all this extension in a very general framework. Okay, so that should motivate us to look at the new approach. So before that, I wanted to make a short detour via what we call the first best case in principal agent problem. So I told you about this principal agent problem. The goal is to study this asymmetry of information between the agent and the principal. And usually what we obtain in that case is compared to a scenario where the principal could force the agent to do whatever is best for her. Okay, so usually we compare this moral hazard, so second best case, to this kind of first best scenario where the principal directly chooses the agent's controls. Okay, and so the idea is that in some cases, the principal may be able to observe the effort of the agent, and then in that case, we may have equality in terms of value for the principal between the first best case and the second best case. Okay, and this would be the case if the principal can design some kind of penalization contract or forcing contract that would force the agent to do the appropriate effort. So basically, if the principal can observe the agent controls, then it can penalize strongly the agent if the agent deviates from that control. Okay, so, and that's usually the case. So once again, if the principal can observe the control, then you may have this equality between second best and first best if you don't have any strong assumptions on the contract. So for example, if you don't need the contract to be positive, then you're allowed to penalize strongly the agent, for example. Okay, so for this very simple example, I just took one-dimensional output process. So the agent can control the drift and the volatility through this control nu over here. And so as usual with this small hazard case, we'll assume that the principal so observe this process X in continuous time. And from this observation can deduce the quadratic variation of the process X. Right, so remember in the contracts in the paper by Dylan, Nizar, and Yaksha, the contract, the optimal contract will be indexed on X and on the quadratic variation through these two parameters Z and gamma. Okay, so basically you have kind of two possible approaches here. Either you directly apply the results so using second order BSDE, and that would work. Or you can already kind of feel that we're close to some kind of first best case, right? Because so the principal observed the quadratic variation, so basically he observed like the effort plus or minus the effort, basically, right? So he can compute the square root of the quadratic variation, and then this would approximately give the effort up to a sign, right? So we're very close to the first best, and we were thinking that there might be something in the middle, right? Like in between these two approaches, like we're not completely second best on the quadratic variation somehow because we observe the quadratic variation, and this may give us some information about the control, and it's not completely first best also. Okay, so the idea of the new approach is that if the principal observes this quadratic variation, then why not look at a slightly different problem where the principal will control directly that quadratic variation and force the agent to choose a control that would achieve the quadratic variation that she wants. Okay, and just in the following, I'll just take Kara exponential utility just to simplify and have some kind of almost explicit result here. So to this kind of alternative problem, so the first step, as I told you, is to kind of formulate a new kind of new problem. Okay, so this new problem doesn't have any economical sense. The main idea is just it's going to be easier to solve, and then at the end we can show that it's going to give the same value as the original problem. Okay, so in this slightly different problem, we're going to assume that so the principal chooses a contract as before, but now also controls the quadratic variation of this process X. Okay, so this there's basically a new control that is sigma here. Okay, and now the agent can still choose its control over the process X, but is constrained to choose some control that would achieve that specific quadratic variation. Okay, so here in that very simple case, the agent has to choose nu such that nu square is equal to the sigma decided by the principal. Okay, and so if you look at the Hamiltonian, you'll have in that case, so the original Hamiltonian, you're maximizing over the effort of, so namely the drift, plus this quadratic variation part. And you can kind of split this maximization between a maximization over the quadratic variation and then a maximization over the effort that achieved that quadratic variation. Okay, so that's, if you look at the constraint problem, then the Hamiltonian you want to have is that second part here. So it's for a fixed quadratic variation, then I look at the optimal effort that I can play, okay, that the agent can play. Here, so it's very simple. You can, of course, compute what's going to be the maximizer of this constraint Hamiltonian. And then using these, you can just rely on BSDEs, so basically follow Sannikov's approach to determine what's going to be the optimal form of contract in that case. Okay, so basically the form is quite similar as before. you have now this constraint Hamiltonian in the Lebesgue integral. You have the ZDX to incentivize the agent to make some effort on the drift. And then, so the last part is just because of Carré exponential utility. You're giving risk to the agent, so you have to compensate him a bit, okay? But the most important part here is the difference. So compared to the contract in the Sannikov's approach, the Hamiltonian is slightly different in the sense that here you have this constraint that a given quadratic variation needs to be achieved. Okay, and so once you look at this kind of form of contract, you have equivalence between the value of this new problem that we artificially introduced and the value of this kind of stochastic control problem, where now basically the principal is going to control the process X and the process Xi through the parameters Z and sigma. Okay. And okay, so it's also quite clear that the value of this first best problem is going to be higher than the value of the original problem, right? Because mainly the principal has an additional control here. Okay, but of course, what we want to show is to show equality here. Okay, so to show equality, as I told you in the first best case, so we have kind of equivalence between the first best and the second best if the principal observes the control and can design a penalization contract, right? So for now, the principal observed the quadratic variation, so we're like, okay, maybe she could directly control it, but we'll have equivalence between the problem only if we can prove that starting from the original problem, we can find a nice contract that would allow the principal to achieve the best case scenario, basically. Okay, and of course, I mean, once you know that the contract from the paper by Dylan, Yaksha, and Nizar are optimal, then that's the one you want to use here, right? So you don't need to prove that they're really optimal through second order BSD here, because they will achieve the best utility possible for the principal. Okay, so you take the contract from the paper by Yaksha, Dylan, and Nizar. You can compute the best response of the agent, and you know that the value of the original problem is going to be higher than the value of the problem when I restrict to this form of contract here. Okay, so you'll have another standard stochastic control problem where the principal choose the Z and the gamma in the penalization contract here. Okay, and now if you want to, I mean, you can look at the two problem we have. So the value of the original problem is smaller than the value of this first best kind of alternative problem. And then the value of the original problem is also higher than this standard stochastic control problem where the principal chooses Z and gamma. Okay, now if you look at these two standard stochastic control problem, it's easy to find a link between the sigma in problem 1 and the gamma in the problem 2. Okay, so you have this kind of one-to-one correspondence between a sigma in in the first best problem and a gamma that you should choose in the penalization contract. Any question?
Yes.
Yeah.
You use the exponential utility.
Yes.
Correct? Is that important?
No. Yeah, so, okay, here it's exponential. What we can do is utility of a contract, like any utility with a discount factor and some cost. So, yeah. Okay. Okay, I'll have a couple minutes to talk about the more general framework. So I think, yeah, I put general utility here, but no discount factor, but you can add the discount factor. But so basically the idea is that we can deal with a more general problem with a drift and volatility coefficient that can depend on the process X and on the effort, of course, but that can be more general than the linear example that I showed you before. And so in that case, you can formulate the original problem as I mean, very similarly as before. So the principal chooses an optimal contract anticipating what's going to be the optimal response of the agent. Okay, and so the idea is very similar to the one I already explained for the specific example. The principal is going to observe x in continuous time, so can deduce the quadratic variation, even if the problem is not just linear and one-dimensional, but this would work in general. And so instead of using this quadratic variation in the contract, so indexed through this parameter gamma, then we could formulate this new problem where the principal will choose to control directly the quadratic variation and force the agent to do this effort that would achieve this quadratic variation. Okay, and so you can write the general alternative problem, so just considering that the effort of the agent are going to live now in a slightly different space, basically forcing this effort, if you look at the quadratic variation, to achieve the one that is fixed by the principal. Okay, and so you have this kind of alternative problem, so the more general problem compared to the one that I showed in the example, but that's a similarity. So in that case, the principal will again control the contract and the control on the quadratic variation, which is sigma here. Okay, and as in the example, we're quite convinced that this first best kind of value is going to be higher than the value of the original problem. But of course, what we want to show is the equality, right? So first, so this alternative problem, as in the example, you can solve it through BSDE. So that's how you can rewrite, basically, I think it's here. Okay, so you can use BSDE to find the optimal form of contract and then rewrite the principal problem as a more standard stochastic control problem, so choosing z in the contract and sigma that correspond to the control on the quadratic variation. And for the next step, so you will do as in the example, you take the contract from the paper by Yakshan, Nizar, and Dilan, you put it in the original problem, and you try to show some kind of correspondence between the z and gamma in the penalization contract and the z and sigma in the first best control problem. Okay, so I think it's, yeah, I'm going a bit fast on this, but okay, maybe I should show this. So basically, this is when the problem when you restrict to the contract form in the paper by Dilan, Yaksha, and Nizar. And so the control problem faced by the principal using this contract is going to be very similar to the one I showed you before, right? So the dynamic of the process X and the dynamic of the process Y, which is kind of the continuation utility of the agent, both will satisfy the kind of same system of SDE here. The only difference is how they're coupled. So they're coupled through the optimal effort of the agent. And in one case, the optimal effort of the agent are the maximizer of the classical Hamiltonian in that case. So they're function of z and gamma that are in the contract. But if you look at the first best problem, then the optimal effort of the agent are maximizer of the constraint Hamiltonian. So there will be function of z and the sigma, that's the density of the quadratic variation. Okay, so basically what you want to do is to show some kind of correspondence between the two problems as we did in the example. And so you look at basically the optimal effort in both cases, and you want to show some link between the sigma and the gamma. Okay, so I mean, intuitively here, if I give you a gamma, then you can compute the optimal effort of the agent with respect to this gamma, so just computing the maximizer of the Hamiltonian. Then you can compute the quadratic variation associated to this optimal effort, and this would basically give you a sigma. Okay, so this would give you the correspondence, and then you can kind of inverse the problem and find the appropriate gamma if you start from an optimal sigma in the first best problem. Okay, and so at the end, you have basically equivalence of all the problems that we define. So the original one, the first best reformulation, and the simplification to standard stochastic control problem. Okay, so all the value would be equal for the principal, and you have that the contracts from the paper by Dylan, Yaksha, and Nizar are optimal here in the sense that they achieve the maximal value for the principal. Okay, and so yeah, so just to conclude a little bit, and then I'll briefly mention what we're doing, so mostly on multi-agent problem, but that's always the same thing, so step 1, 2, 3. But so first, just to summarize, so we're kind of formulating an alternative first best problem. This problem doesn't have any sense, like economically, right? But we can solve it just using BSDE, and then we can show that that's the maximum value that can be achieved by the principal, and that it can be achieved through some contracts. And so the hope is that with this new approach, because we don't need second order BSDE, then probably we can extend it a little bit more in a more straightforward way to tackle some kind of extension to multi-agents or mean field type of interaction between the principal and the agent, and also to like processes with jumps or things like this. Okay, so for the model with multi-agent, just to give you an idea of like very simple example, but we're doing a more general thing, of course, in the paper. But the idea is exactly the same, right? Like, so you have a process that is controlled by two agents, let's say A and B. So agent A choose alpha, agent B choose beta here. Then the principal observe the process X in continuous time and can look at the quadratic variation, but the quadratic variation is basically going to be given by alpha plus beta squared, right? So the principal cannot distinguish the individual effort, just the sum of the effort squared. Okay, and so if you look at exponential utility also to simplify, then okay, so yeah, so you will start by formulating this kind of first best problem. So the principal would offer a contract xi A for agent A, xi B for agent B, and control the quadratic variation of the process X. And the agent would, you will look for a Nash equilibrium between the agents, right? So you would look at control alpha and beta from agent A and agent B, such that their sum squared will achieve the quadratic variation that is fixed by the principal. Okay, and same as before, so you can play a bit with the Hamiltonian, and you can compute what's going to be the best response of agent A to whatever agent B has done and to a contract. So the contract will be indexed by some ZA and ZB for each agent. Right? So you can play with this. You can characterize the set of Nash equilibrium here. So that's going to be actually any control alpha and beta such that their sum squared achieve this quadratic variation. Okay, and so step 2, same. So you have your reformulation of the problem. Then you can use just BSD or multidimensional BSD to characterize the optimal contract in that case. And you will find similar form to what we've seen before, where now the Hamiltonian you want to put is the constrained one because of the constraint on the quadratic variation, and also at the Nash. Okay, and so you can rewrite the problem as a stochastic control problem here. So now you have just 3 state variables. So X is the common process that is controlled by the agent, and the principal also controls the contracts xi A and xi B for each agent. Okay, and same, now you want to show that this value is going to be achieved. So you want to design a proper contract for that. And same, so inspired by Yaksha, Dylan, and Nizar, you take kind of their form of contract, so indexed through Z and through this other parameter gamma with the Hamiltonian that is at the Nash in the Lebesgue integral. You put this into the agent problem, and you show that the maximizer are given, or the Nash is going to be given by a fixed point of the Hamiltonian. So you can easily compute this here. You have some kind of condition that appear just to make sure that there exists a Nash, otherwise you may not have any Nash here. And you can, at the end, obtain the 2 problems, as in the one agent example we've seen before. So similarly, you can find a link between basically the z tilde here and the sigma in the first problem. And okay, I think the link is quite easy when you write it like this. And so you have this one-to-one correspondence between a sigma in the first best problem, or kind of first best problem, and the z tilde here is some kind of function of the gamma, right? So this gives you some kind of link between the z and the sigma. Okay, and so I guess I'll almost conclude, but so we're basically looking at a more general multi-agent framework compared to the very simple example that I gave you here. So basically like multi-dimensional dynamics, multi-dimensional output process X, general reward function, so that was your equation, Renee, I guess. So we can look at, expected utility with a discount factor, so the u doesn't have to be exponential, but it has to be invertible, I guess, if we want to recover the form of the contract. And general reward for the principal, and once again, the steps are exactly the same as before, so it's a bit repetitive already. And so that's to be continued, and I'm closing with this, I'm sorry. I could stay polite for 40 minutes. I'm sorry? No. Saint-Étienne, yes, but.
So these foreseeing contracts, whatever they are realistic? Are they just a mathematical tool to get this best to second best? Are they more than
so what do you mean by realistic? I think, okay, I think there is one paper that mentioned that in econ, like the indexation on the process X and the quadratic variation is kind of like this kind of managerial contract where you index on the profit, but also like an option on the profit. So I don't know if that sounds realistic, but that's implementable in some situation.
it's interpretable?
Yeah.
Sorry, an even more naive question. And if the principal observes the agent only in discrete time, so the problem is continuous time, can you do something? Is what you are building epsilon optimal, for instance, or something like that?
Yeah, so I don't know. I think, so the problem, so if you look at this problem in just one period, then usually you won't have any optimal contract. So people restrict the study to this kind of linear contract because in continuous time it works. I guess if you have a discrete time observation, then probably you can formulate your contract as like, a sum of your observations. So z xi at each point I that you observe, and you can also probably approximate the quadratic variation by the sum of the increment squared. So this would be a good guess for the contract at first, but checking convergence and this, I don't know.
More questions?
Thanks.